let's jump right into this explainer. Today, I'm putting on my senior structural engineer hat to run a deep dive audit on cable management design. We aren't just drawing lines on a blueprint today, we're looking at the rigorous physics of cable tray support distance. Because getting your span right before you hit that order button, that is the literal difference between a resilient infrastructure and a catastrophic site failure. Let's get to work. There's this incredibly dangerous and honestly costly misconception out there in our industry. It's the idea of choosing support spacing based solely on tray form or thickness. As an engineer, it physically pains me to see this happening on job sites so often. Look, just because a tray looks robust or the steel feels extra thick absolutely does not mean you can just string it up however you want. Form simply does not guarantee structural integrity if your underlying span geometry is flawed. Here's our engineering briefing for today. We're going to methodically dismantle this misconception by looking at common design mistakes, the structural mechanics of span, the 4 core variables you actually need to track, how to handle chaotic field conditions, and finally benchmarking and standards. All right, starting off with Section 1, Common Design Mistakes and Costs. I literally cannot stress this enough. What you see for a catalog span does not equal actual structural performance. Blindly trusting a manufacturer's maximum span without accounting for your specific engineering variables is just a fast track to structural failure. You have to remember, catalogs offer a baseline under perfect, controlled laboratory conditions. Out in the real world, if you just lift a span number off a page without auditing the actual environment it's going into, you are taking a massive financial and safety risk. Moving right along to Section 2, the structural mechanics of span and capacity. Now let's look at the actual physics, because this is where the rubber meets the road regarding system capacity. We're comparing the exact same tray carrying the exact identical cable load. At a 1.5 meter support span, it's perfectly rated and totally safe. But double that distance to 3.0 meters, the entire system becomes dangerously compromised. The physical width and weight haven't changed at all, but doubling that span exponentially multiplies the bending moment and the stress on the metal. In structural engineering, your span entirely dictates your bearing capacity. You just can't cheat the math. Which brings us to Section 3, the 4 core variables determining spacing. True structural integrity really requires a holistic engineering framework. To get the correct spacing, you have to look way beyond just checking a tree's thickness. You need to simultaneously evaluate 4 things: the tray type, the physical weight of the layout, the specific environmental load, and the overall structural geometry. If you ignore this multivariable reality and buy based purely on how sturdy something looks, you are practically guaranteeing a structural failure. This breakdown brilliantly illustrates the structural range we're working with. As you can see, support span capabilities shift drastically depending on the system type. Light wire baskets inherently require much closer support spacing, mainly due to their flexible nature. Conversely, your heavy-duty letter trays are specifically engineered to bridge much longer gaps. You absolutely cannot apply ladder tray math to a wire basket. Your span has to respect the structural reality of the tray you're actually using. So, okay, we have our theoretical math mapped out, but the really crucial question is this. How does this perfectly calculated lab data hold up when it hits the messy reality of the job site? What happens when our pristine designs meet the actual elements? That leads us perfectly into Section 4, Engineering Challenges of Field Conditions. As structural specifiers, we know full well that the environment always gets a vote. Outdoor runs introduce wind loads and ice accumulation. That adds massive, totally unexpected weight to your span. Heavy mechanical vibration from nearby machinery, that can cause severe fatigue over time if your supports are spaced too far apart. Complex fittings change the load distribution entirely, and vertical drops require completely different bracing strategies. Any single one of these factors will immediately force us to overhaul our baseline support plan. And finally, Section 5, Benchmarking Structural Performance in Quotes. This is such a crucial point when you're in the procurement phase. When reviewing bids, you must strip away the marketing fluff. You absolutely have to normalize competing supplier quotes so you are strictly comparing apples to apples structural performance. Think about it. If supplier A is quoting a system assuming a 3.0 meter span, and supplier B is quoting based on a much safer 1.5 meter span, their prices will look wildly different, but they aren't offering the same structural capacity. You have to normalize that data to ensure the engineering integrity is identical before you even glance at the price tag. To ground this in reality, the source material highlights a company called Xinma. They manufacture compliant cable tray systems, busway, seismic bracing, and intelligent cable management solutions. And notice where their products are actually used: data centers, rail transit, industrial plants. These are incredibly high-stakes environments where structural failure is simply non-negotiable. When we evaluate systems from a supplier operating in intense environments like that, we demand adherence to foundational numbers. And the major baseline here is IEC 61537. But that IEC standard is really just the beginning. A true structural solution is validated by its compliance with a whole host of rigorous international standards. Xinma's products, for example, comply with IEC 61537, NEMA VE1, BSEN 500085, and GB 31251. As an engineer, I can tell you these aren't just random letters and numbers. They are documented proof that the system will actually survive the severe physical loads, bending moments, and span limitations we've been talking about today. I'm going to leave you with a final thought to take back to your drafting tables. The next time you're reviewing a design or signing off on a complex cable run, honestly ask yourself, are you just designing for the catalog, or are you truly engineering for reality? Because as we've explored today, understanding how support distance impacts your overall system capacity is the only real way to build infrastructure that lasts. Thanks for joining me on this explainer. Keep engineering smart, and I'll catch you next time.